We start from the beginning at the program counter, which in this case is an enabled 32-bit register. After resetting the processor using the reset switch, the program counter then outputs into the read-only memory, which fetches a corresponding instruction. The instruction is split up into its various parts. The left bits are used as the opcode for the control unit, and the right 6 bits are used as a function code. The control unit contains a collection of Karnaugh maps that enable the right components to execute the instruction. It also feeds into the ALU to give it a function. The reg file component is a collection of registers which can output the value of a register corresponding to the read address inputs, which are RA1 and RA2. Also, the registers can be written to using the write address, WA3, and the write data, WD3, provided the write function is enabled by the control unit with the WE3 input. The ALU then calculates an address that can be looked up in the data memory. Again, the data memory can also be written to with the data from the reg file and the address from the ALU, provided the write function is enabled by the control unit. The ALU can also create data that is immediately passed into the next component. This is the case, for example, in add immediate. This is dependent on the mem to reg output from the control unit. If this is low, the value is taken directly from the ALU, else if it is high, the output of the ALU is considered an address which is looked up and read from the data memory. This value is then taken in as the write data for the reg file. And provided that write enable is high, the data is written to a specific address determined by this 5-bit multiplexer. Parts of the instruction, specifically the write half, are then passed into this sign extender, which fills out the left bits with either a 1 or a 0, depending on what the leftmost bit of the input was. The output of the sign extend is then passed into a multiplexer, which may pass it on into the ALU depending on the initial instruction. It is also passed into a left shifter, which essentially multiplies the input by 4, and this is then combined with the program counter incremented by 4, shown here. This is then cut and combined with other parts of the instruction, and again this is fed into the jump multiplexer here, which handles input into the program counter in the event of a jump. This is given by the control unit. There is also a similar multiplexer which feeds into the jump multiplexer, which handles the input in the event of a branch instruction. This is determined by the control unit, as well as the 2 inputs from the ALU being equal. That concludes one cycle of the clock, and with the program counter now being adjusted by the increment and also by either a jump or branch instruction, the new program counter can then fetch the next instruction from the ROM and continue the cycle.
The arithmetic logic unit takes 3 inputs, 2 32-bit A and B arguments, and a 3-bit F argument that determines a function that the ALU will run on A and B. It can run AND, F is equal to low, 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 or F is equal to low, low, high, plus F is equal to low, high, low, and not F is equal to high, low, low, or not F is equal to high, low, high, minus F is equal to high, high, low, and set if less than F is equal to high, high, high. It outputs the result of the operation chosen by F on A and B over here. For example, if we follow through the AND operation on the circuit, F is equal to low, low, low. The S input for the 32-bit 2-input multiplexer is 0. The carry input for the 32-bit 2-input adder is 0. And the S input for the 4-input 32-bit multiplexer is also 0. So that means that the 2-input 32-bit multiplexer chooses the A input over here, so that means it chooses the B argument. That means that the carry input for the addition between A and B is going to be 0, and that means that the 4-input 32-bit multiplexer chooses the A input, because on a 4-input multiplexer, 0, 0 is A, 0, 1 is B, 1, 1 is C, and 1, 0 is D. Therefore, the output of the 32-bit 2-input multiplexer is B, which feeds into the 32-bit AND gate, as well as the 32-bit adder. The A input feeds into both of these blocks as well, of which the outputs are respectively A and B and A plus B. A and B then feeds into the A input of the 32-bit multiplexer, and A plus B then feeds into the C input of the 32-bit multiplexer, the 4-input 32-bit multiplexer, which then chooses its A input, so it chooses A and B, and then outputs A and B. So therefore, we have confirmation that when F is equal to 0, 0, 0, the ALU outputs A and B. We actually wrote two functional versions of the square code. The first version was 22 lines and used a separate square loop to multiply numbers manually. It used 5 registers and ran very slowly, and it slows down as the numbers get bigger, but it worked properly and we actually calculated square numbers. The second version of the MIPS code we wrote takes advantage of an algorithmic property of square numbers. For example, adding the odd number 1 to the square number 0 produces the next square number 1, and adding the next odd number 3 to the square number 1 produces the next square number 4, and so on. So it uses 3 registers, and it runs much quicker than the first version. Both versions are written to reset when it reaches 100 squared, so there's no chance that the numbers will go off the edge of the 7-segment displays that we have on our FPGAs. The second version is 8 lines long, and its initialize reset function sets $T0 to 1, $T0 is an odd number counter, $T1 to 1, $T1 is a square number value, and $T2 to 10,000, $T2 is the maximum value for its square values. Its loop function displays the square numbers on the 7-segment displays, and it sets the square number value to the odd number value, increments the next odd number value by 2, checks if the square number value is less than the maximum value, and if it is, it sends back to the initialize/reset function, and otherwise it loops around again.